Welcome, focused learners. If you're gearing up for the Physical Sciences Paper 1 exam, well, you are in exactly the right place. Consider this explainer basically your ultimate weapon. Today, we're not just going to sit here and review physics concepts, we are going to actively decode the exam itself. We'll look at exactly how examiners test these foundational laws and, more importantly, how they try to trick you. Because let's face it, they definitely try. By the end of this walkthrough, you're going to have the tools and the confidence to walk right into that exam room and completely own it.
So here's our game plan for today's explainer. We'll start with our Welcome to Exam Power, and then we're going to dive into mastering mechanics and forces. From there, we hit energy, momentum, and work. Next up is waves and the Doppler effect, followed closely by electromagnetism and modern physics. And finally, we'll wrap the whole thing up with some final Paper 1 tips to keep you sharp.
Welcome to Exam Power.
Okay, let's dive into this. Exam prep can feel, honestly, incredibly overwhelming. But the secret? The secret is realizing that the test isn't some big mystery. It's really just a structured puzzle. And you know what? We have the blueprint. Just look at this official header from the May/June 2025 Paper 1 exam. Seeing this right now might give you a little spike of adrenaline, maybe some prep anxiety, and hey, that is totally normal. But I want you to look at it and realize it's literally just paper. It's 150 marks over 3 hours, and it's built entirely on rules you already know. Our goal today is to bridge that gap between just knowing the physics and actually knowing how to answer the physics questions.
Section 2. Mastering Mechanics and Forces.
Mechanics. This is where the foundation of your paper lies, and it's exactly where examiners absolutely love to test if you truly understand the definitions or if you've just, memorized them. Take a look at this scenario straight from the past papers. A bucket is at rest on a table. Which one of the following is the reaction force to the weight of the bucket as described by Newton's third law? This, my friends, is a classic examiner trap. It looks so unbelievably simple, but it catches thousands of students out every single year.
So, I want you to hit pause on this explainer right now. Seriously, look at the question, commit to an answer in your head, and then hit play. Active recall, forcing your brain to actually make a decision before hearing the answer, is one of the most powerful exam prep techniques you can possibly use. Go ahead, predict the answer. Now, what's really interesting about this slide is that big red X over on the left side. Most students immediately jump to the normal force. They think, okay, the bucket pushes down on the table, so the table pushes up on the bucket. But wait, the question didn't ask for the reaction to the bucket pushing on the table, did it? It asked for the reaction to the bucket's weight, and weight is defined as the gravitational force the Earth exerts on the bucket. Therefore, according to Newton's third law, which requires pairs to act on each other, if the Earth pulls the bucket down, the true reaction force has to be the bucket pulling the Earth up. It sounds kind of weird to say out loud, but it's physically accurate.
Section 3. Energy, momentum, and work.
Let's carry that precise logic right into our next trial, collisions. This is a section where keeping your definitions straight is literally the difference between getting a 0 and getting full marks. Here is your ultimate collision cheat sheet, visually mapped out for you. Definitely commit this to memory. First up, momentum is only conserved if the system is isolated, meaning no external forces are interfering with it. Second, total momentum is conserved in both elastic and inelastic collisions. However, kinetic energy, that's the dividing line. In an elastic collision, kinetic energy is totally conserved. But in an inelastic collision, kinetic energy is lost to heat, sound, or deformation, so it is not conserved.
All right, challenge accepted. Let's test that immediately with question 1.4 from the 2025 exam. Two hard objects collide inelastically in an isolated system. Which one of the following statements is correct for this collision? You know the drill by now. Pause the explainer, consult that cheat sheet in your mind, and lock in your prediction.
Let's move to and see how this builds step by step to protect you from those tricky traps. Step 1, the question clearly states the system is isolated. That immediately tells us total momentum must be conserved. Step 2, it specifically says the collision is inelastic. Referring our rule, inelastic means total kinetic energy is not conserved. Therefore, combining these truths, the only correct multiple choice option is the one stating momentum is conserved, but total kinetic energy is not. By breaking the question down into these defined steps, you make it basically impossible for the examiner to trick you.
Section 4, waves and Doppler effect.
We are making great time here. This next section is a brilliant, high-yield topic that often mixes waves with elements of astrophysics. And yeah, that can look pretty intimidating on the page. But first, let's establish the baseline.
The Doppler effect is simply the change in observed frequency because the source and the observer are moving relative to each other. Think about it. If a source moves toward you, the waves compress and the frequency goes up. If it moves away, those waves stretch out and the frequency goes down. That is the core principle right there.
Now let's apply that exact same concept to the cosmos with question 1.6 from the 2025 paper. We're observing absorption spectra. The spectral lines for star B are more redshifted than those for star A. The question asks, how do the frequencies of the observed spectral lines and the speed of star B compare to star A? Go ahead, pause and predict. Have fun with it, and really think about what redshift practically means for movement before you hit play.
Okay, so redshift means the star is moving away from Earth, which stretches those light waves. If star B is more redshifted, it means its waves are stretched even further because it is moving away at a greater speed. And because the waves are stretched more, the observed frequency drops lower. So comparing B to A, the observed frequency is lower and the speed is greater. If you just trace the physics step by step through our grid here, option C becomes the undeniable answer. See? Not so intimidating when you break it down.
Section 5. Electromagnetism and Modern Physics.
Entering our final technical phase, we look at modern physics. I know, it often feels super abstract, but strict definitions are going to save you here. Look at question 1.10 from 2025. Which one of the following statements correctly describes the photoelectric effect? You've got 4 options involving photons, electrons, emitting light, colliding, or being ejected. Hit pause, use the process of elimination, and make your choice.
Let's break down exactly what happens at the atomic level. The photoelectric effect is the specific phenomenon where light, packaged as a tiny photon, hits a metal surface. An electron inside that metal completely absorbs the photon's energy. If that energy is high enough, pop, the electron breaks free and is ejected from the surface. It does not involve electrons emitting light, and it definitely doesn't describe electrons colliding with each other. Therefore, the statement, an electron absorbs the energy of a photon and is ejected from the surface of a metal, is the only technically accurate description. Option C for the win.
Section 6. Final Paper 1 Tips. Well, we've traversed mechanics, energy, waves, and modern physics. Let's zoom out a bit and recap our core tactics. So the crucial point is, 1. Always hunt for the phrase isolated system. It's your green light for conservation laws. 2. Never confuse a normal force with a Newton's third law reaction pair. They test entirely different interactions. 3. Circle inelastic or elastic the second you see them. And to round out the rest of your paper, for vertical projectile motion, pick one direction as positive and stick to it. For electric circuits, remember that adding resistors in parallel decreases total resistance. For electrostatics and magnetism, let your right-hand rules guide you. And always, always actively eliminate wrong answers.
You've put in the work. You've walked through the traps, the concepts are solid, and your strategy is razor sharp. When you sit down with that exam paper, read carefully, trust your foundational logic, and let your knowledge shine. I'll leave you with one final thought today. With all these newly sharpened tools in your arsenal, what score are you going to claim when you walk into that exam room? Go get it.